Today, we're going to dive into a disease that impacts hundreds of millions of people and animals. But this isn't just a straightforward medical brief. It's the wild, almost unbelievable story of a parasite and its epic body-hopping journey across species. So let's get right into it. Okay, to kick things off, let me throw a puzzle at you. Picture a herd of cattle. They start developing this really strange condition. Their breathing gets so blocked up that they make this constant, loud snoring sound. I mean, what on earth could be causing something so specific, so weird? The answer? It's a tiny, parasitic flatworm, a blood fluke. It's kind of hard to wrap your head around, right? That an organism you can't even see can cause that much chaos? But hey, welcome to the absolutely fascinating world of parasitology. All right, so let's get formally introduced to the microscopic villain at the very heart of this story. The disease itself is called schistosomiasis, and it's caused by these flatworms, the schistosomes, that have evolved to live inside the blood vessels of their hosts. And right off the bat, there's a super interesting biological twist. See, most flukes like this are hermaphrodites, but not schistosomes. They have separate male and female worms. And this little detail is actually a huge deal for their life cycle. To really, truly understand this parasite, we have to follow its incredible multi-stage life cycle. Think of it like a high-stakes journey. It's super complex, it's incredibly dangerous for the parasite, and it all begins with a single egg. So it all starts here. You've got adult worms just hanging out in the veins of a mammal, and they're producing eggs, lots of them. These eggs then get passed out of the host in its feces. But for the whole story to continue, that egg has one critical mission. It absolutely has to land in fresh water. No water, no next generation. It's that simple. So assuming the egg makes it to water, it hatches, and out comes this little guy, the miracidium. It's this microscopic, free-swimming larva, and it is on a frantic search. The clock is ticking, because it only has a few hours to find and burrow into a very specific kind of freshwater snail. If it fails, that's it, journey over. But if our little miracidium succeeds, it hits the jackpot. It enters what is basically a parasite factory. Inside that snail, it morphs into something called a sporocyst, which is essentially a living sac that just clones itself over and over and over, turning that one single invader into thousands. It's the parasite's force multiplier, a brilliant, if terrifying, evolutionary strategy. Okay, so after this population explosion inside the snail, the next generation is unleashed back into the water. These are called cercariae. They're tiny larvae with a distinctive forked tail. And these are the ones you have to watch out for. They are the infectious stage, swimming around with one single purpose: find a mammal. And this brings us to the final incredible act of the invasion. The cercariae don't need a cut, they don't need a wound, they can drill right through perfectly healthy skin. It's kind of crazy. Once they're in, they change form again, hit you right in the bloodstream, and eventually settle down in the veins to mature into adult worms. And boom, the cycle is complete, all set to start over. So we just followed the parasite's amazing journey. But what's actually happening inside the host's body this whole time? Well, you might think the adult worms are the big problem, but the real damage, that comes from something else entirely. And this is the absolute key to understanding the disease. The adult worms, they're actually pretty sneaky. They learn to hide from the host's immune system while living in the blood vessels. The real danger, it comes from the eggs. A lot of them don't make it out of the body. Instead, they get swept away in the bloodstream and get stuck in vital tissues, like the liver. So what makes these trapped eggs so dangerous? Well, as this quote explains, the eggshell isn't perfectly sealed. Little proteins from the larva inside, what scientists call antigens, they leak out. And to your immune system, those proteins are like a giant red flag, screaming, "Intruder!" which triggers an all-out attack on the egg. This constant immune assault leads to something called granuloma formation. Your body literally builds these hard capsules of inflammatory cells around each and every egg to try and wall it off. But imagine thousands of these forming in an organ like your liver. It's a disaster. It's a case of friendly fire, creating chronic inflammation that leads to a buildup of hard scar tissue, a condition called fibrosis, which just slowly chokes the life out of the organ. And this whole process can look really different depending on where those eggs happen to get lodged. If they get stuck in the liver, you get what's called intestinal schistosomiasis, which can lead to a severely scarred, non-functional liver. If the eggs get trapped in the nasal veins of cattle, you get those cauliflower-like growths that cause the snoring disease. And if you're a person who gets penetrated by a cercaria that was actually meant for a bird, your immune system kills it right there in the skin, and you get a nasty, itchy rash we call swimmer's itch. So, how in the world do you fight a parasite with such a clever and resilient life cycle? Well, it's a massive global health challenge, and the strategy has to involve attacking the parasite at every single stage of its life. The fight is basically waged on four main fronts, and each one is designed to break a link in that life cycle chain we just talked about. We use medication to kill the adult worms in people and animals. We try to control the snail population to get rid of that essential middleman. We improve sanitation to stop the eggs from getting into the water in the first place. And we educate communities on how to stay safe. And taking out that intermediate host, the snail, is a huge piece of the puzzle. You can go the chemical route, using things called molluscides in the water. You can go biological, maybe introducing natural predators that eat the snails. Or you can go physical, just by fencing off ponds and lakes where these specific snails live. And really, here's the main takeaway from all this. That complex life cycle, the very thing that makes the parasite so successful, is also its greatest weakness. The thing that makes it so resilient is also its Achilles heel.
2. That's the number. It needs two hosts, a snail and a mammal. If you can break the link between those two, if you can interrupt that handoff, the parasite literally has nowhere to go. You stop it cold.
This really drives the point home. You have to have a multi-pronged attack. Drug treatment is critical, snail control is critical, sanitation is critical. There's no single silver bullet here. Real success only comes when you hit the parasite from all sides at once. Now, before we wrap up, there is one last bizarre twist to this whole story, something called concomitant immunity. It's this strange biological trade-off where having adult worms already in your body actually gives you some protection. The immune response they generate is enough to stop new larvae from successfully setting up shop. Think about that. It's a type of immunity that only works as long as you're still infected. It's just a perfect, weird example of the complex relationship between a parasite and its host. And that leads us right to our final thought. Schistosomiasis is, at its core, a disease of the environment. It's about water, snails, and sanitation. So as our planet changes, as temperatures rise and rainfall patterns shift, the habitats for these snails could expand, or they could move. So the big question we're left with is this. In a rapidly changing world, how do we adapt our fight against this ancient enemy?